Welcome to EE662. We were talking about the substations, and we talked about the substation equipments and how they operate. From this point onwards, so we are going to talk about the substation grounding. Okay, so the first we will take a look at like why the substation grounding is that important. Okay, so the grounding, even in the home you put a earth wire and you do the grounding in order to protect your equipment. So the same way, the substation grounding is important to make sure that there won't be any high current flowing through the equipment that can cause the damage to them. So if you there is a high current flowing due to any fault or anything, so you have to make sure that current should go to the earth through this grounding arrangement. Okay, so that's the one purpose, and the other purpose is to provide the safety or to the personnel that are working in the substation. Okay, so make sure that if anybody touches anything like a chassis of the transformer or any uh, the towers or anything, you have to make sure that there won't be any current flowing through the excess current flowing any current flowing through the body, which can damage the worker. Okay, so those are the two purpose that you need the substation grounding. Okay, so this substation grounding system, it include interconnected grounding facilities. Okay, so which include you have the ground grid buried underneath the earth. Okay, and then you have the overhead ground wires. Okay, and then you also have the neutral conductors and underground cables, and you have the foundation and deep well, etc. Okay, so all these components are included in the grounding system. Okay, so safe grounding required the interconnection of yes, interaction of two grounding systems. Okay, so the first one is the intentional grounding. What we call the intentional grounding is that the system consisting of the grounding system buried at some depth below the earth's surface. So this is the grounding that we intentionally put in the substation. So you have these the ground mesh underneath the earth's surface. Okay, and there's another type of grounding called the accidental grounding. Okay, so this grounding is the grounding that happens in temporarily. It's established by a person exposed to a potential gradient in the vicinity of the ground facility. Okay, so when you are in the substation, when you are working in the substation, for an example, if you touch anything, there could be a the ground path created through your body. Okay, so this type of a thing is called the accidental grounding. So we have to make sure that when an accidental grounding happen, that will not harm any person who create this accidental grounding. Okay, so because these voltages are depend on the substation and the site, so it's not easy to design one grounding system that is acceptable for all locations. Okay, so you have to be a little bit specific to the location, because this grounding system, it's depend on the area, as well as the soil type of the ground where you establish the substation, and those parameters. Okay, so these parameters that are affected the voltage in the substation, so these are some of the parameters. So the grid current is the one thing, fault duration, and soil resistivity, surface material, and the size and the shape of the grid. So this all matters for to creating this grounding voltage, and then uh, the voltage in and around the substation. Okay, so when you are designing a substation, you have to consider all these parameters. Okay, so let's take a look at the accidental grounding. Okay, so we can define a couple of grounding circuits. So first one is called the touch voltage. Okay, so you can see that there is a person and there's a structure uh, in the substation, and then you have the station grounding in here. Okay, so over here you have the, okay, let me take this pencil first. Okay, why this is not working? Okay, okay, sorry about that. So my this the tablet was not working properly. Okay, give me a second. Okay, so we were talking about the some definitions when talking about the accidental grounding. So you have this what you call the, okay, so the touch voltage and the step voltage. So first let's talk about the touch voltage. So the touch voltage is defined as the fault current being discharged to earth by substation grounding system and a person touching a grounded metallic structure. So if there is a person working in the substation touches this metallic structure in the substation, so there could be a fault current going through uh, the person to the ground like this. So you have the fault current in here, and the sum of the fault current will go through the structure to the ground. So since the structure is connected to the ground, and then there could be some, if the grounding is not properly done, there could be some currents going through the body of the person as well, which we define as the IB. So the fault current is known as IF, and the current going through the structure is known as IS. Okay, and the step voltage is defined as the current going through the human body, because you step, if you are like this, and then your steps, you have a gap between two steps, and then there could be a potential difference between this point and this point, which can lead the current going through your body back to the earth due to the potential difference between these two. So that is called the IB. Okay, so this can happen if the grounding system is not properly done. Okay, okay, so that way you can any worker in the substation or anybody in the substation can experience the body current flowing through. Okay, so we can define an equivalent circuit for the touch voltage. So first we will talk about the touch voltage, and then we will talk about the step voltage. Okay, so the Thevenin's equivalent circuit for the person's for the touch voltage is defined like this. So you have the uh, okay, so what you have in here is as in the above diagram, you have the structure. Okay, and some sort of a structure, and then there is a person. Okay, and sorry, my bad. Okay, everything is gone. Okay, so you had this structure, and then the person in the here, and he's touching this one. Okay, so there is a fault current going, and this fault current will go through the body. Okay, and then in the legs it can go in two different paths. Okay, so because of that, so this point below act as a parallel circuit. That's why this says the feet in parallel. Okay, so you have the body, the one whole thing, and series with that you have two legs in parallel. So basically if you draw the resistance, what you will have is something like this. Okay, so connected to the ground potential. Okay, and so that's here that's, there's a current flowing in here called the IB. Okay, so with this configuration we can define the Thevenin's equivalent circuit for touch voltage like this. So this is the terminal H and this is the terminal F. So if you remember, this is the terminal H and here is the terminal F. Okay. Uh, okay. So and then the RB is the body resistance. So you have this Thevenin's equivalent circuits where the VTH is the voltage between terminal H and F when the person is not present. Okay, so when the person is not present, the typical voltage that should be between H and F is defined as VTH. Okay, so IB is the body current. Okay, so the IB is the body current, and when the ZTH is equivalent to the resistance of 2 feet in parallel, so this ZTH is equal to the impedance of the 2 feet in the parallel. That means this part. Okay, we can define the touch voltage as E touch is equal to IB times RB plus CTH. Okay, so then the resistance of the foot in ohm is represented by the, so we can represent the resistance of the foot, okay, by a metal circular plate of radius B. So you have a circular plate, something like this, okay, with the radius B, uh, in meters on the surface of a homogeneous earth of resistivity rho. Okay, so this is the earth and this is rho. Okay, so this feet can be represented in this kind of an arrangement. So then the resistance of the feet in ohms is defined as rho over 4b, where the b is the radius of this metallic circular plate. Okay, so typically we can assume that b is equal to 0.08 and rf is equal to 3 times rho. Okay, so then for the Thevenin's equivalence impedance of the 2 feet in parallel is defined as CTH is equal to RF over 2 for the touch voltage. So this is for the touch voltage. Okay, so there's something going on. Okay, touch, for touch voltage case you can define the CATH as RF over 2, which is equal to 0.5 times rho. If we take the RF is equal to 3 times rho. Okay, okay, so similar way for the step voltage you can also define the similar equations, but now in this case so you are like this. So say you have this and 2 feet, okay, the ground, and now the current is going like this. So now so you have one resistor here and then the body the upper part resistance, and then you can think of it like like this. Okay, so all are in series. Okay, so that's why it says the feet in series and series with the body, because now the current is generated at this point and going through the other feet. Okay, so so with that arrangement we can define the step voltage E step to be equal to IB times RB plus CTH. So keep in mind that this CTH and the previous CTH are two different values. Even though we use the same notation, it has two different values. Okay, because earlier case the two feet were in parallel and now the two feet are in series with the rest of the body. Okay, so so with the same representation as we discussed earlier, representing the foot as a metal circular plate with a radius b, we can define the resistance of the foot in series, which is equal to rho over 4b. Okay. So again, if we assume that b is equal to 0.08 and the RF is equal to 3 rho, for typical case, we can define the CTH for the step voltage case. So this is for step voltage case, 2 times RF, okay, because these are now in series, okay. So you have 6 times rho. So earlier these were in parallel, so you have the RF by 2 RFs in parallel, and so you had this value, and here 2 RFs are in series, so you get the CTH is equal to 2 RF, which is equal to 6 times rho if the RF is equal to 3 times rho. Okay. Okay. So those are the two definitions on touch voltage and the step voltage. Okay. So when talking about the grounding system of the substation, so you in the substation typically you have this what we call the surface layer. Okay. So what you have is the earth in the substation, and then you have all the substation equipment, and if you have gone to a substation, you might have seen there is another layer of gravel or something. Okay. So if you have been to a substation, you know what I am talking about. Okay. So there is another layer of some material. uh, Typically what you find in the substations are gravels, and then you have all the substation equipments on top of this. Okay. So this layer uh, act as a derating layer. Okay. So what you have in here is a uh, high resistivity material, okay, spread throughout the earth surface in the substation. Okay. So this will reduce the current flowing through the body if there is a touch potential or step potential happens, because now the resistance of this one is high compared to the ground, so that will create a high resistive path to the ground. So because of that, the current flowing through uh, the body will, for an example, if you have a person sitting like this, touching this one, because this thing is now connected to the ground, so you have this what we call the ground mesh underneath the earth surface, and all these are connected to the ground mesh, and you are not connected to the ground mesh directly, but through this high resistive surface. Because of this higher resistance, now you will experience lower current flowing through your body. Okay. So that's the purpose of this the surface layer. So then we define what we call the surface layer derating factor, CS. Okay. So which basically increases the resistance between foot and the ground. Okay. So you can define the with the this surface derating factor CS, you can define the foot resistance RF. Earlier we had this rho over 4b, which was rho was the resistivity of the earth, but now you have the before comes the earth, you have this the surface layer with the resistivity of rho s. So now you have rho s over 4b, and then you have to multiply that by this derating factor in order to calculate the foot resistance. Okay. So because now it has been increased. Okay. So this equation can be used to calculate the derating factor, where the K is equal to rho minus rho s divided by rho plus rho s. Rho is the resistivity of earth, and rho s is the resistivity of the surface material. Okay. And then this Rm2NHS is the mutual ground resistance between the two similar parallel coaxial plate separated by a distance 2nh in an infinite medium of resistivity rho s in ohms meter. Okay, so that means that will represent the resistance between the earth and the this surface layer. Okay, so so with all these parameters you can calculate the surface layer derating factor by using this equation. Okay, so but you can see that it's a little bit there's a little bit complex equation. Okay, so with the assumption of b is equal to 0.08 meters, and we can calculate uh, the derating factor by using this equation as well, kind of a simplified equation. So the results are in the tolerance range of 5%. Okay, so the results you obtaining from this equation is within 5% of the results that you obtain from this equation. So this will give more accurate results, but this will give good enough results for your design purpose. Okay, so you can plot the h's, which is the height of the thickness of the surface material in meter. Okay, so what you have in here, so that is this thickness is called the h's. Okay, so that is h's, and then the so how the surface derating factor varies with the thickness of the surface layer, and the parameter k is defined by this graph. So you can find you can calculate the value of k by using this equation, and depending on the k value you obtain and the thickness of the gravel, you can find the corresponding for an example, if you go like here, and if the k is equal to 0 minus 0.1, then you have the derating factor of this much. If the k is equal to, like for an example, this is 0.2, this is 0.3, then you can find the corresponding derating factor by using this graph for your design purpose. Okay, okay, so that's some definitions and the some parameters that you use for the design of the substation grounding. Okay, and so let's see, like uh, so what are these permissible body current limits? Okay, so when you talking about the touch potential and the step potential or touch voltage and step voltage, we talk about the body current, IB. Okay, so what is the permissible, the body current that can be handled by a human being? Okay, so so when you talk about the body current, the duration, magnitude, and the frequency of the current affect the body as the current passing through it. So all these three factors affect the human body when the current is passing through the human body. Okay, so the most dangerous impact on the human body is known as ventricular fibrillation. Okay, so ventricular fibrillation is something that when the high current is flowing through your body, your heart will suddenly stop. Okay, so then your heart will stop. That means there is no pumping of the blood. So that means almost instant death, but you can recover it by giving another electric pulse to the heart. So you might have seen in the many movies that people are doing this. They put that they rub something together and apply a charge between and put them in the heart. So you will give another pulse, and then you can recover the functionality of the heart. So but if this happen for a longer period of time, that means that can cause death. Okay, so this is the most dangerous impact due to the current flowing through the body. Okay, Okay, so the threshold of the perception, the detection of a slight tingling sensation is generally recognized as 1 milliampere. So if the 1 milliampere current is flowing through your body, then you will feel a slight tingling sensation, like, no, something, I don't know, like itchy or something. Okay, but that won't do any harm to your body. Okay, and if the current is between 1 and 6 milliampere, we know it as a let go current. That means if you are touching something, then you when the current is flowing through the body, you tend to grab it. Okay, so if you are touching it in the in the direction of where you can grab that one, then you tend to grab it. Okay, for an example, if you have some sort of okay, what happened again? Okay, so some metal thing. Okay, and then you are touching it, let's say, I don't know, like this. I'm not a good drawer, but your palm is in this side. So this is the metal one, and then when the current is flowing through your body, your fingers will, you know, uh, quench, and then you will grab this one. Okay, so if the current is between 1 and 6 milliampere, you can still let it go. Okay, by, by applying some, you can do something and let it go if the current is between 1 and 6 milliampere. I think you get what I am talking about. Okay, so, and if the current is between 9 and 25 milliampere, you lose the muscular control. Okay, so that means you can't control your body anymore, and because of that, when you grab this one, then you may not be able to let it go. Okay, so that means the current will continuously flow through your body, unless the trip is gone or something else happen, because you can't let this go. Okay, so, and then if the current is in the range of 60 milliampere to 100 milliampere, then this ventricular fibrillation will happen. Okay, so as I said, the only way to restore the normal heartbeat is through the another controlled electric shock, which is called the defibrillation. Okay, so, okay, so that's what will happen when the different amount of body current will flow through your body. So you have to make sure that always the current going through the body, even in a fault conditions in a substation, is below a certain limit, at least below uh, this limit, below 6 milliampere or so, you still can let it go. Okay, and if you go into this level, that means it will create a catastrophe. Okay, okay, so it definitely has to be below the ventricular fibrillation value, but it's better if you can go through, if you can design it such a way that the current is much less than this value. Okay, okay, so not only the magnitude of the current matters, but the time that the current flowing through the body is also matter. So we can define an equation to determine the allowable body current by using this equation. Okay, so IB is the body current, is equal to K over square root of TS, where the TS is the duration of the current exposure. Okay, and the K is the square root of SB, where the SB is it's an empirical constant. That means a constant determined by the observations and the measurements related to electric shock energy tolerated by a certain percentage of a given population. Okay, so you take the population, take the sample, and you define a certain presentation like 90% or 97% or something, and then according to that you can calculate how much of electric shock that the people can handle. Okay, so based on that the typical K values has been calculated for the K is equal to 0.116 if the body weight is approximately about 50 kilogram. If the body weight is 70 kilogram, K is equal to 0.157. Okay, so you can see that the fatter you are, you can handle more current, right? So that's a one advantage of being fat. Okay, I don't you can think about it. Okay, then the equation is based on test limits to values of time in the range of 0.03 to 3 seconds. So this equation is valid for the TS between 0.03 and 3 seconds. Okay, so there are other equations defined for different time values for more the larger range, and so all these equation narrow down to the give the similar results of the IB within this range. Okay. Okay, so let's talk about the some definitions on this is which we talk about is the allowable body current. So now let's see the tolerable voltages. Okay, so we can define certain uh, what we call the certain parameters for this one. So the first one is called the ground potential rise, or the GPR. So this is the maximum electrical potential that a substation grounding grid may attain relative to a distance grounding point assumed to be at the potential of remote earth. Okay, so if you have the substation, uh, okay, so you have the substation, and then outside the substation some remote location, because in the substation you have all these substation equipments, transmission line going on, and then there's electrical fields, magnetic fields, so which will create this ground potential. Okay, but in the far away in the substation you have a normal typical ground or typical earth. So this is the earth resistance at that typical earth, what we call the remote earth. So you can think of this as a zero potential. Okay, and then the maximum potential uh, the substation can have compared to this remote earth is known as the uh, what we call the ground potential rise. Okay, so in this case this is the maximum voltage that can have uh, for uh, for this substation. Okay, okay, so so this GPR is typically a product of the magnitude of the grid current. Okay, so the grid current matters, and the portion of the fault current conducted to the earth by the grounding system, so that also matters, and the ground grid resistance. So you have the ground grid in here, and that resistance also matters. Okay, okay, and then there's something called the mesh voltage. So this is the maximum touch voltage within a mesh of a ground grid. Okay, so here you have the mesh voltage. So at this point, so EM, so this is the maximum voltage, maximum touch voltage uh, of a mesh in the substation. Okay, and then there's something called the metal to metal touch voltage. So in this diagram you can see there's a two metal structures in the substation, both are connected to the ground, okay, or the substation grid, grounding grid, and then somebody touch these two, so there is a potential between these 2 points, which is called the metal to metal touch voltage. Okay, okay, so this is typically assumed to be negligible in conventional substations. Okay, because both the points are grounded, so the potential difference, if there's any, is very small, so you can neglect that part. Okay, and then you have the step voltage as we discussed earlier. So when somebody is going here, so if the steps are spread uh, for distance of 1 meter, okay, then there can be a step voltage generated between this field, okay. uh, and then the other one is the touch voltage, the same thing that we discussed earlier as well, okay. uh, so the potential difference between the ground potential rise and the surface potential at the point where a person is standing, while at the same time having the hand in the contact with the ground surface, is defined as a touch voltage, okay. So you can see here, that the step voltage is also very small, but the touch voltage can be high, okay. And this mesh voltage is also high, okay. And then you have something called the transferred voltage. The transferred voltage is defined as a special case of the touch voltage, where a voltage is transferred into or out of the substation from O to a remote point external to the substation site, okay. So now you have this outgoing conductors white the in the substation, and then if you accidentally touch something, and then there is a voltage generated at that point, so which is known as the transferred voltage. So this transferred voltage is typically not just related to the GPR of the particular substation that the person is in, but also depend on the GPR of the remote substation where this transmission line is going, okay. So because of that, there could be a high voltage difference, and there could be a high current going through the body, okay. So anyway, in the maximum voltage of any accidental circuit must not exceed the limit that would produce a current flow through the body that could cause fibrillation, okay. So you have to make sure that any of this case the voltage should not exceed, so you know V is equal to IR, so this is IB. So from that you can calculate the B. R is the body resistance, and you can calculate this one, okay. So you have to make sure that there won't be any high current flowing due to this potential difference that can cause a ventricular fibrillation, okay. So that's the main requirement when you design the substation, okay. So to wind up this part, let's take a look at another variable called the tolerable voltage, okay. So assume that the uh, a 50 kilogram person with the body weight of the 50 kilogram is typically have the body resistance of 1000 ohms, okay. Then we define the tolerable touch voltage, okay, as by using this equation. So tolerable touch voltage for 50 kilogram person is defined by using this equation, okay. uh, and the tolerable step voltage for the 50 kilogram person is defined by using this equation, okay. So these are the tolerable voltages. So if you know for the typical body weight and the resistance, body resistance, here you can say it's RB or something, then you can calculate the allowable voltage, tolerable voltage, okay. And based on that you can design the substation protection, okay. So since the only resistance for the metal to metal touch voltage is the body resistance, then you don't have that all those parts, so this should be 0.116 divided by root TS, okay. This is for metal to metal touch, okay, for a 50 kilogram person, okay. So Okay, so this shock duration Ts is usually assumed to be equal to the fault duration. So unless the fault is cleared by a some other means like a circuit breaker or something like that, so this the current will flow through the body. So this Ts is assumed to be equal to the fault duration. Okay, so if the reclosing of a circuit is planned, then the fault duration time should be the sum of the individual faults and used as the shock duration time. Okay, so if you have this reclosing facilities, then you have to so there could be there's a fault in this period, and then it's open and then reclose at this point, and then fault continues, open it, reclose, and something like this. So then you have to consider the addition of all these as the uh, shock duration. Okay, okay, so with that you can calculate the tolerable voltages, and with the tolerable voltages you can uh, design the ground voltages that should be in the substation. Okay, okay, so with that I will pause this lecture at this point, and then next we will talk about the design criteria for a substation grounding system.